Okay, so today we will discuss the few problems based on the ratio test. Using the ratio test, we can solve those problems, and also we will discuss the few of the results which are also needed for further study. So, let us see, we have gone through the ratio test. The ratio test says that if a n be a sequence of positive numbers, if a n's are sequence of the positive numbers of positive real numbers, and if limit of this a n plus 1 over n as n tends to infinity is say L, and when if L is greater than 1, then limit of this sequence a n as n tends to infinity will be diverging and diverges to infinity. And the second part of it shows that if limit of this L lies between -1 and +1, then the limit of a n as n tends to infinity is 0. And particular case is when a n's are, when L is less than 1, then in that case we are negative, then we will see that all negative terms, then we can apply, take the minus sign and get the results, okay, for alternative. So, let us see the exercise based on this. Suppose it is given that we have the sequence, one is find limit of a n as n tends to infinity, where a n's are is of the form n to the power p x to the power n, where p is positive or negative rational number, where p is a rational number, positive or negative rational number, rational numbers, okay, and x is a real quantity, x is real, x is real. Okay. Now, if we look this, apply the formula. So, what is a n plus 1 over n? If we look this, it comes out to be 1 plus 1 by n raised to the power p x. Now, when n tends to infinity, p is fixed. So, this term will go to 1, and basically the limit of this when n tends to infinity is nothing but x. So, when x is greater than 1, so according to the ratio test, if the limit of a n plus 1 over n is L, where L is greater than 1, the limit of a n will be plus infinity. When L lies between -1 to +1, the limit will be 0. So, limit of this a n over n is infinity if x is greater than 1 and 0 for x lying between -1 and +1. Okay. And when x is equal to 1, then it reduces to the form n to the power p, and the behavior of n to the power p we have already there. If p is positive, it will go to plus infinity. When p is negative, it will go to 0. So, when x is 0, it is equivalent to the limit n to the power p as n tends to infinity, which will be plus infinity if p is positive and minus infinity and 0 if p is negative, and for p is equal to 1 also it will be. Okay. So, this is, and when x is less than equal to 1, if x is less than or equal to minus 1, then what happens? This sequence mod x n less than equal to 1, the sequence is minus 1 to the power n, minus 1 to the power n, and then it will keep on oscillatory and oscillating. So, the mod of a n will go to plus infinity and n's are is an oscillatory infinite. Oscillatory infinite. Okay. Similarly, when p is negative, when p is negative, then in that case also the same thing happen. It is again this will be x greater than 1, it is infinity, x lying between minus 1 is 0, and for other it. So, the same results as 1, same as 1. Okay, that is one. So, this will give the. Okay. Second exercise, let us see. So, exercise 2, suppose find the limit of x to the power n factorial n as n tends to infinity, where x is any real number, any real number. Now, again apply the ratio test. So, why ratio test? What happens to this? A n plus 1 over a n as n tends to infinity, it comes out to be what? Limit of this as n tends to infinity x over n plus 1. So, whatever the x may be, this limit will go to 0 for any x real. It means this limit will always be 0 for all x. Okay. Third, find the limit of this, limit of factorial n to the power 1 by n as n tends to infinity, factorial n 1 by n. Now, to solve this limit, let us use the previous one. We know the limit of x to the power n factorial n is tending to 0, is 0 when. So, use exercise 2. So, from exercise 2, it implies that factorial n goes much faster than comparative to x to the power n. That is, this is always be greater than n for n sufficiently large, say n naught, because then only it because it is tending to 0, it means the denominator is going much faster to infinity comparative to x to the power n. Therefore, it will factorial n will be greater than x after a certain stage, say n is greater than n naught. Therefore, x factorial n to the power 1 by n will be greater than x, and this is true for any x, for any x belongs to R. It means the limit of this thing, limit of this factorial n to the power 1 by n as n tends to infinity will exceed to any number a, will exceed to any number a for any positive number a howsoever large, and this shows this is only possible, the limit of this is infinity. Limit of this will be infinity. So, it will be followed by this. Okay. Now, this can exercise 4, find the limit of limit of n when n tends to infinity, where n is 1, 3, 5, then 2n minus 1 over 2, 4, 6 up to 2n. Suppose this is our n. Okay. Now, these are all positive terms. So, apply the ratio set by ratio test a n plus 1 over n. This comes out to be what? 2n plus 1 over 2n plus 2. N plus 1 is n plus 1, 2n plus 1 and 2n plus 2. So, the limit of this as n tends to infinity is the limit of this as n tends to infinity. Divide by n. So, when you divide by n, it comes out to 2 plus 1 by n over 2 plus 2 by n, and limit as n tends to infinity, and that will come out to be 1. It means the limit of this n as n tends to 1 is convergent, and we goes to limit is 2n plus 1 by 2n. Okay. This limit what is this is 1, sorry, is 1. Now, what the ratio test says? The ratio test, if you look the ratio test says when n is a sequence of positive numbers such that limit n plus 1 over n is L. When L is greater than 1, limit will be plus infinity. When L lying between minus 1 to 1, limit is 0. But it does not say anything about L is 1. When L is 1, the series, the sequence a n may converge, may not converge, because it depends on the type of the sequence. We cannot say the limit is 0 or limit is infinity or limit is finite. We have to compute that. So, here the ratio test fails. Here ratio test fails. We are unable to get it. So, what to do? Then in that case, we have to apply our previous knowledge. That we know if a sequence which is a monotonically decreasing or monotonically increasing sequence, and if it is bounded, monotonic increasing bounded above, monotonic decreasing bounded below, then such a sequence will definitely have a limit. So, let us find out whether this sequence is a monotonically sequence or not. Now, here if we look 2n plus 1 over n, this comes out to be 2n plus 1 over 2n plus 2. It means that this is total thing, this total is less than 1, since the ratio n plus 1 over n is coming to be 2n plus 1 over 2n plus denominator is higher than the numerator. So, ratio is strictly less than 1. So, it means the nth term is larger than n plus 1. So, when n 1, 2, 3 etcetera, it keeps on decreasing. Therefore, the sequence a n is a monotone decreasing sequence, is a decreasing sequence. Okay. And since a n's are all positive, and since a n's are positive, so it decreases and at the most it will go to positive number. So, and so sequence a n is convergent. This is one thing which is clear from this concept. Okay. We are interested in finding the limit now. So, it is that convergence part is clear, that the sequence has to converge, but what will be the limit that is. So, let us see the a n's again. What is a n? A n was 1, 3, 5 up to 2n minus 1 over 2, 4, 6 up to 2n. Now, can you not say it is less than if I write 2, 3 is 4, 5, 6 up to 2n, okay. And this part I am just increasing 3, 5, 7, 2n plus 1. So, this term, because 1 is less than 2 or 1 by 2 is less than 2 by 3, you can say like that. So, 1 by or 2 is less than, so 1 by 2 is greater than 3, 1 by 3 is greater than 1 by 2, and like. So, this will be 1 by 2 is less than 2 by 3, 3 by 4 is less than 4 by 5, 5 by 6 is less than 6, and like this. So, we can say this is less than, because half is less than 2 by 3, 3 by 4 is strictly less than the 4 by 5, and continue. So, we can say this. Okay. So, n is less than this, n is this. So, n square will be less than the product of these two, 1 3 5 2n minus 1 2 4 6 2n into product of this 2 4 6 2n divided by 3 5 7 2n plus 1, and that comes out to be 1 by over 2n plus 1. So, n square is coming to be 1 by 2. Therefore, the limit of n square is tending to 0, because n's are positive. So, limit cannot go negative, it can go at the most 0, and n square is less than this. As n is sufficiently large, the limit is tending to 0. So, it means the n limit must go to 0 as n tends to infinity. So, that will be the answer for this. Okay. So, this is what. Now, there are others also, but before going few, let us take one result which is given by the Cauchy, and so before going this, let us see the result which is known as the Cauchy's first theorem on limit. On limits. So, what this theorem says, if the sequence a n converges to L, then the sequence x n, where x n is a 1 plus a 2 plus a n y n, also converges to L. Also converges to L. Let us result 1. Okay. Can we put it as an exercise also, but because this is a standard result, so we can say put it as a result 1. So, what he says is, if suppose a n sequence are convergent, then their mean, arithmetic mean, basically it is a arithmetic mean of this will also converge to L. That is the first result. So, let us see the proof of this result or solution of this. What is given is a n converges to L as n tends to infinity. It means the difference between a n and L, that is, for a given epsilon L greater than 0, there exists an n naught such that the mod of a n minus L is less than epsilon L for n sufficiently large. Okay. So, what we can do we can say that, so we can assume or we can take a n's as L plus epsilon n, where epsilon n is convergent, this sequence is convergent and tending to 0 as n tends to infinity. So, when n tends to infinity, the sequence epsilon goes to 0. It means a n minus L can be made as small as we please after a certain stage. Okay. So, let us suppose. Now, consider x n. So, consider x n. X n is a 1 plus a 2 plus a 3 a n divided by n. So, substitute a 1 in terms of epsilon 1. So, what we get is, if I substitute a 1 is L plus epsilon 1, a 2 is L plus epsilon 2 as n. So, this is n times L divided by L. So, L plus epsilon 1, epsilon 2, epsilon n divided by n. Okay? We get this. Now, we wanted the sequence x n goes to L. It means, if I prove that this second term goes to 0 as n tends to infinity, then it will. So, required to prove is the sequence epsilon 1, epsilon 2 plus epsilon n divided by n. This sequence basically converges to 0 as n tends to infinity. This is once we prove, then x n will go to L. Okay. Now, since epsilon n is a convergent sequence, converging to 0, So, it is a bounded sequence. So, it is bounded sequence, because every convergent sequence is bounded. So, there exists a k such that mod of epsilon n is less than or equal to k for all n. There exists a positive k just. Okay. And further epsilon n tends to 0. So, we get, and further since epsilon n tends to 0 as n tends to infinity. So, for a given epsilon greater than 0, there exists an n naught such that mod of epsilon n can be made less than epsilon for n greater than equal to, say, n naught. Okay. Now, consider this one. Consider mod of epsilon 1, epsilon 2, epsilon n divided by n. Now, this will be less than equal to mod epsilon 1, epsilon 2 plus epsilon n naught divided by n plus epsilon n naught plus 1, epsilon n naught plus 2 up to epsilon n divided by n. Okay? I have chosen this. Now, when n is greater than n naught, the mod of epsilon n is less than, it means each of this term is less than epsilon. So, total becomes n minus n naught. So, this will be less than n minus n naught times n minus n naught times, and then this is what this is equal less than epsilon divided by n plus. Now, this term, each term is bounded by k. So, this is bounded by k. It means, this is less than n naught times k divided by n, is it not? Now, n naught k, if I choose, n naught is fixed, k is fixed. So, if I take epsilon such that n naught k by n is less than, say, epsilon, then what happens? So, if this is less than epsilon plus epsilon, provided n is greater than n naught k by epsilon. If I take n to be greater than this, then this part is less than epsilon, this is less than 1. So, this is already less than epsilon. So, total is less than 2 epsilon. So, this part, when n is sufficiently large, goes to 0. Then once it goes to 0, then this sequence x n will go to L. So, x n will go to L as n tends to infinity. Is it okay? That is right. This is the first Cauchy theorem on the limits. The second Cauchy theorem, that is the result 2. which is also we call it as a Cauchy's second theorem on limit. On limits. What this theorem says is, if sequence n be a sequence of positive number, sequence of positive number, and limit of n plus 1 divided by n as n tends to infinity is L, and limit of this is say L, then limit of n to the power 1 by n as n tends to infinity will also be L. So, that gives means if the ratio of these sequences is L, then the nth root of this n will also have the limit L. So, let us see the proof of this. Okay. What is given is that this ratio is L, given a n plus 1 over a n, limit of this as n tends to infinity is L. It means that is for given epsilon greater than 0, there exists say m such that mod of a n minus a n plus 1 over a n minus L is less than epsilon for all n greater than equal to m. Okay. So, what it means, this implies that a m plus 1 y a m, this term lies between L minus epsilon and L plus epsilon. Okay. Now, if we continue this, a m plus 2 by a m plus 1 lies between L plus epsilon, L minus epsilon, and like this up to say nth term, which is a n over a n minus 1 lies between L minus epsilon, L plus epsilon. Just continue. Now, find the product, because these are all positive quantity, remember, because a n is a sequence of positive, these are all positive, greater than 0, greater than 0, greater than. So, this is also positive. So, once they are positive, we can multiply without getting the change in their inequality. Okay. So, when you multiply this thing, what you get? These are total n minus m terms. So, here we get L minus m. So, this implies that L minus epsilon to the power n minus m is less than, if you multiply this. So, the cross this telescopically getting cancelled. So, a n over a m is left only. So, a n over a m, and which is less than L plus epsilon to the power n minus m, okay, where n is greater than m. Now, divide by L minus epsilon to the power minus m. So, if I divide, because this is positive quantity. So, again when you divide, so this implies that, which implies that L minus epsilon to the power n is less, L minus a is less than, if I divide by this, then what you are getting? A n over a m, n over m into L minus epsilon to the power m, because this will come, because this is positive, because L minus epsilon is positive. So, we can do like that. Now, take the power 1 by n. So, what we get from here is, and similarly, when you take L plus epsilon to the power n, here also we get this is greater than a n over a m, a n over a m into L plus epsilon L to the power m. Okay. Now, this part L plus m is greater than 1, sorry, this a n by m. So, now from here again, so what we get basically, so we get, therefore, we get L minus epsilon L to the power n is less than a n over a m, n over a m, L m is less than L plus epsilon L to the power n, just like, is it not? So, that is not. Now, take this term here. So, we get L minus epsilon a n a m over L m, okay, raised to the power 1 by n into L minus epsilon L into L minus epsilon L is less than a n to the power 1 by n, which is less than a n a m over L to the power m raised to the power 1 by n L plus epsilon L. Okay. Let it be 1. Clear? Now, since limit of this a m over L to the power m by 1 by n as n tends to infinity is 1. Why? Because this is fixed a m, sorry, the a m fixed point, L m is also fixed. So, this is some constant power 1 by n. So, when n is sufficiently large, the limit will go to 1. It means, this term will lie between 1 minus epsilon L and 1 plus epsilon L. Okay. So, we can say that this limit, entire thing L minus epsilon L, this part can be. So, we can say this limit 1. So, what we get is, therefore, this entire thing lies between here. So, therefore, we get L minus epsilon L minus epsilon L is less than a m by L m, a m by L m raised to the power 1 by n L minus epsilon L, L minus epsilon L, which is less than L minus epsilon L plus epsilon L. Why? Okay. This a m minus 1 by L, because it is this entire thing lies between L minus epsilon L and then minus 1. Okay. So, this will be this one tending to 1 basically. So, this limit will go to L minus epsilon L only basically, L minus S. So, this total thing will lie L minus epsilon L minus 1 and L minus 1 epsilon L. Similarly, this term will also lie between the, similarly we can say L plus epsilon L, L plus epsilon L minus epsilon L less than a m over L m raised to the power 1 by n L plus epsilon L, which is less than L plus epsilon L plus epsilon L. So, what we conclude is that if I look this entire thing a n to the power 1 by n, a n to the power n, the lower bound will be L minus 2 epsilon L. This will be the lower bound, and for n by 1 by n, upper bound will be this. So, this 1 and 2 if we combine, then we get from here is L minus 2 epsilon L is less than n to the power 1 by n is L plus 2 epsilon. So, as n tends to infinity, the limit of this n to the power 1 by n, limit of this is nothing but L, and this proves the result. Okay. Now, here when it is L is in when L is greater than sufficiently large, then this limit will go to infinity also, infinity in fact. Okay. So, that is now as a corollary to these results, as an exercise we can say if a 1 A2, A1, A2, A etc. is a sequence of positive number numbers such that n goes to L, n goes to L, where L is greater than 0. Then A1, A2, An raised to the power 1 by n goes to L. So, let us see the solution of the A1, A2 is a sequence of positive numbers such that limit of An is L, where L is positive. Then the nth root of this product, that is geometric basically geometric mean of this will also tends to L. The solution based on the previous Cauchy theorem, first theorem on the limit, that if An goes to L, then the mean value of A1 plus A2 plus An by n will also go to L. So, here we assume that if An converges to L, then log of An will go to log L. This is our assumption. Here assume that if An goes to L, then log of N will go to log N. In fact, this we will show it that log is a continuous function when N is positive, of course, well defined. Then continuous function has a property that it transfers the convergence sequence to the convergence sequence. So, log, because of it is a continuous function, so it will transfer the convergence sequence to convergence. But here, since we have not gone to the continuous function so far, so let us assume here that when An goes to L, then logarithm of this will also go to L. Okay. Now, so it is given. So, this is now given because An is given. So, we can assume that log N goes to M. Apply the Cauchy's first theorem on limit. So, what we get? Their mean, that is log of geometric mean of this second, sorry, this is the second theorem. So, apply the mean of this first theorem, we will get the first theorem, yes. So, log of A1 plus log of A2 plus log of An divided by n will also go to log L by that theorem, but this product is nothing but the log of A1, A2, An, and power 1 by n will go to log N by property of log. So, this shows that as n tends to infinity, Okay. So, this implies limit of this A1, A2, An raised to the power 1 by n as n tends to infinity will be, and that proves the result for it. Okay. Now, let us see the other exercise. If S1, S2 are positive, and Sn plus 1 and S1, S2 are positive, and Sn plus 1 is half of Sn plus Sn minus 1, half of Sn and Sn minus 1, then prove that the sequence is S 2n plus 1 and sequence S 2n are both monotone. The one increases, another decreases, okay, are both monotone, and find the limit of this. Okay, find the limits. limit. Okay. So, let us see the solution for it. What is given is that given S n plus 1 is half of S n plus 1, S n minus 1, sorry, S n minus 1. This is given. So, let us assume S 1 and S 2 are two number, where S 1 is greater than S 2. Let us assume this. So, S 3 from here is S 1 plus S 2, no, S 3. So, n is equal to 2. So, S 2 plus S 1 by 2. This will be the S 3. It means between S 1 and S 2, here is S 1, this is S 2. Here we are getting S 3, which is the average of this, the mean of S 1 and S 2. So, we get S 1 greater than S 3 greater than S 2. Okay. Similarly, now S 4 is nothing but what? When n is 3, we get S 3 S 2 by 2. So, S 4 is lying between what? Because this S 3 and S 2, in between S 3 and S 2. So, we get there is S 1 greater than S 3 greater than S 4 greater than S 2, and like they continue this. So, what we get? So, we get a sequence which have this S 1 is greater than S 3 greater than S 3 greater than S 4 greater than S 2 greater than S 5 greater than S 4 greater than S 2, like this. Say 5 term, what will happen? 5 is 4 plus 3 S 4 plus S 3 by 2. So, S 4 S 3, in between S 3 and S 4 it will lie, and like this. So, what we get? That when a suffix are odd, S 1, S 3, S 5, it is decreasing. When suffix are even, it is increasing, S 2, S 4, S 6 and so on. So, basically this implies the sequence of the odd numbers S 2 n plus 1 is a monotonic decreasing sequence. While the sequence 2 n is a monotonic increasing sequence. S 2 n is a monotonic S 2 n, that is the same S 2 n. So, this is and S 3 S 5, it is a yes decreasing, and S 2 n is monotonic increasing sequence. So, we get this is a monotonic decreasing and monotonic increasing sequence. So, convert now when it is a monotonic decreasing sequence, but it is bounded below by S 2, but bounded below by S 2, because S 1 S 2 are fixed. So, it is convergent. S 2 n is again decreasing, S 2 is increasing, but it is bounded above by S 1, bounded above by S 1. So, this shows that both the sequence are convergent. So, both are convergent sequence. Then whether they will converge to the same limit or not, let us see. So, if we consider this difference S 2 n plus 1 minus S 2 n, consider this difference. So, what we are getting is half S 2 n plus S 2 n minus 1, because S 2 n apply the formula, minus S 2 n. So, that comes out to be minus half S 2 n minus S 2 n minus 1. It means, when you take S 2 n plus 1 minus S 2 n, it is half of the S 2 n minus S 2. So, continue this. If I continue this, then what you are getting? You are getting S 2 n plus 1 minus S 2 n, basically comes out to be what? Minus half raised to the power, that is minus half raised to the power 2 n minus 1, 2 n minus 1 S 2 minus S 1. Okay. S 2 n minus 1. Now, this will be equal to S 1 because S 1 is greater than S 2. So, we can take half 2 to the power n minus 1 S 1 minus S 2. Now, this is positive, but this is fixed. Here this will go to 0. So, it tends to 0 as n tends to infinity, because half is less than 1, and therefore, both the sequence limit of this S 2 n plus 1 as n tends to is the same as limit of S 2 n as n. Okay. So, both converges to the same limit, say L. Okay. Now, to find out the limit of this, okay, so we get to find L, we consider 2 S n plus 1 S n twice S n plus 1 plus S n. This will be equal to what? S n plus S n minus 1 plus S n, because S n plus 1 is S n plus S n minus 1 by 2. So, 2 of this. So, this will be equal to what? 2 S n plus S n minus 1. Now, as n tends to infinity, this S n plus 1. Okay. Now, again when you take 2 S n plus 1 is S n is 2 S n. Similarly, if I continue this process, what we get? This is also equal to, in the final term, we get 2 S 2 plus S 1, because this is so this is equal to basically this. So, as n tends to infinity, this will give 2 L, this is L equal to 2 S 2 plus S 1. Therefore, L becomes S 1 plus 2 S 2 by 3, and that is the answer for it. Okay. So, this clear. So, we get. Now, I will write few problems that will be used as a tutorials. So, one can try those problems. Okay. So, tutorials, and then you can find the solution, which is very easy. Okay. Say first example, we have to do this part using the epsilon delta definition, using the definition of limit of a sequence to establish the following, using the establish the following limits. Limit of this as n tends to infinity is n square minus 1 over 2 n square plus 3 equal to half. Okay. N square plus 1. Second B is limit as n tends to infinity 3 n plus 1 over 2 n plus 5 is 3 by 2, like this. Okay. Limit third, limit of this minus 1 to the power n into n divided by n square plus 1 is 0 as n tends to infinity. Okay. Then limit of this, that is all. Now, if we look that without epsilon definition, we can just find the limit very quickly. So, n is sufficiently large. So, when we substitute n infinity, infinity by infinity indeterminate. So, what we do is we divide by n square and get the result 1 minus 1 by n square 2 plus 3 by n square. So, when n is sufficiently large, it becomes 1 by 2. But how to get the result? Say hint, suppose I wanted to for was. So, for any epsilon greater than 0, for given epsilon greater than 0, find n naught such that mod of this part n square minus 1 2 n square plus 3